Welcome back. The bell problem for today is from your previous lesson 1.1. Describe each pattern and draw the next figure. Okay, so if you look, we start with 1, then we go to 4, then we go to 9, then we go to 16 little boxes. Describing the pattern, you should notice that 1, 4, 9, and 16 are perfect squares, so the next figure should be a 5 by 5. 1.2 is properties of real numbers. At the end of this lesson, you should be able to graph and order real numbers and identify properties of real numbers. Some vocab terms you need to know are rational numbers, numbers that can be written as a quotient of integers. So some examples would be just whole numbers, 2, or it can do fractions, 3/4, etc. Irrational numbers are numbers that have a decimal representation that neither terminate or repeat. The most common are pi and radical 2. Rational numbers and irrational numbers form a set of real numbers. We have real numbers and we have imaginary numbers. You can graph every real number as a point on the number line. If you notice, the number line starts with 0 in the middle, and going to the right you have whole positive numbers, and going to the left you have whole negative numbers. When you're plotting your points, just plot them approximately. If they are a whole number, plot them on the point. If they are a fraction or integer, you plot them approximately. So this one here would be in between -1 and -2. If we were to identify these as rational or irrational numbers, -4 would be a rational number, -1 1/2 would be a rational number, 0 is a rational number. Radical 5 would be an irrational number, because if you type that in your calculator, you would get a decimal that does not stop or repeat. And 4, finally, would be a rational number. To classify some of our real numbers, we start with the natural counting numbers. So start with 1, 2, 3, and going up from there. Then you add the whole numbers, which you just add the natural numbers and then add 0 at the front. Integers are the natural numbers, their opposites, and 0, so like what we had on the number line in the previous slide. And then we have rational numbers that are fractions, or decimals that repeat. So if you look here, we have -1/2, 2/3, 5/4. Any number that can be written as a fraction is a rational number, or any number that has a decimal that repeats, like 0.22 or 0.3333, okay? Someone that repeats. And as you look on the right, the irrational numbers, like I said before, the most common ones are radical 2 and pi. Think to yourself, what are some other numbers that you could write as irrational numbers? Just to classify them some more, rational versus irrational numbers. Rational numbers can be written as quotients of integers, again, as a fraction, or they can be written as decimals that terminate or repeat. Irrational numbers cannot be written as a quotient of integers, and also cannot be written as decimals that terminate or repeat. And again, quotient is the answer after you divide one number by another. So 12 divided by 3 equals 4. 4 is a quotient. Just think of quotient as fraction and you'll be fine. So let's determine whether they are rational or irrational. Let me go back to the slide here. Number 1, we have 1.5, rational or irrational. Hopefully you thought to yourself rational. Even though it has a decimal, it does stop or terminate. Number 2, we have 0.333. As you notice, our decimal is repeating, so that is also rational. 3 is pi, so that's our most common irrational one. 4 is a fraction, 3/4, so that is also rational. And 0 will always be rational. So graphing real numbers on a number line, we have -5/4 and radical 3. My suggestion to you is to find a calculator and type in -5/4 into your calculator and come up with the decimal that it represents. The decimal that it represents is -1.25, so find -1. It's obviously going to be between -1 and -2, but it'll be closer to -1 because it's not greater than half. So we'll plot our point there. Then type in the square root of 3, and you should get a decimal that doesn't repeat, so 0.1732050808. So it's greater than 1, but less than 2, and since it is greater than half, we're going to plot it closer to 2. Again, if it's not a whole number, just plot it approximately. So looking at the next example, we don't have to put them in our calculator. We have the numbers 3, so that one's easy. Don't have to estimate where that goes. And then we have 0.258. So that's less than 1, but greater than 0. So we'll plot it closer to 0. And again, just approximate is fine. Our next one shows the table of lowest elevations of 6 continents. Which list shows the elevations from lowest to highest? Now remember, these are negative numbers, so our first number should be the greatest number if we took the absolute value of it. So it should start with negative 408, and then the number should get less from there. So our answer should be D. Notice how our numbers get smaller and smaller. Even though it doesn't make sense because we're going lowest to highest, they are negative numbers. The bottom example, which list shows the numbers in increasing order? That means we need to go from lowest to highest again. So we need to look to see which one starts with the least negative number. And since we have two negative numbers, 0.5 and 0.2, this makes it really easy because only one of them starts with negative 2, so our answer is C. Next, how do you compare radical 17 and 3.8? My suggestion would be take 17, put it in your calculator, and figure out what that decimal representation is. Since it is 4.1 approximately, that means, if we wrote this out, radical 17, right around in here, radical 17 is greater than 3.8. If you have trouble with greater than or less than, you can take the numbers and put them in your calculator. Say you subtracted radical 17 minus 3.8, you should get a positive number. Since you get a positive number, that means that number is greater than. Just some of the properties of our real numbers. I'm not too concerned if you know these or not. Just remember how they work. Okay, so closure works for addition and multiplication when you're adding up two numbers. Commutative, if you notice, we just switch A and B's places. Associative, we are combining together two different numbers, but we still get the same answer. Identity for addition means whenever you add something to it, you still get the same number back. So the only thing we can add to it will always be 0. And for multiplication, when you're multiplying, obviously you can only multiply by 1. Inverse is easy, because if you have A, the opposite of a positive A would be a negative A. And for multiplication, it's like dividing by A. And distributive property you should know, if you have a number or anything outside of your parentheses, you need to distribute to every single term inside your parentheses. So we need to identify the property that the statement illustrates. The first one, 7 plus 4 equals 4 plus 7. Again, if you need to, refer back to the last slide, and you should notice it looks like the commutative property. All we did is positions of our numbers. So the first one is commutative. And the second one, if you notice, we are dividing or multiplying by the opposites, so like the inverse. So B would be inverse property. Okay, so looking at for opposite operations, this will help us in the future when we're solving our equations. If we're trying to get rid of addition, the opposite will be subtraction. And then if we have subtraction, the opposite is going to be, sorry about that, addition. Opposite of multiplication will be division. Opposite of division is multiplication. And the opposite is square, meaning like x squared, like our Bell problem from yesterday, is the square root. Okay, so use the properties and definitions of operations to show that these I'm not going to really worry about. We know they get the right answer. Again, this is your homework. We will work on it in class tomorrow. Again, if you're not going to be in class, make sure you have it ready when you come back.